In geometry, an altitude of a triangle is a line segment through a vertex and perpendicular to a line containing the base. This line containing the opposite side is called the extended base of the altitude. The intersection between the extended base and the altitude is called the foot of the altitude. The length of the altitude, often simply called the altitude, is the distance between the extended base and the vertex. The process of drawing the altitude from the vertex to the foot is known as dropping the altitude of that vertex. It is a special case of orthogonal projection. Altitudes can be used to compute the area of a triangle. 1/2 of the product of an altitude's length and its base's length equals the triangle's area. Thus, the longest altitude is perpendicular to the shortest side of the triangle. The altitudes are also related to the sides of the triangle through the trigonometric functions. In an isosceles triangle, the altitude having the incongruent side as its base will have the midpoint of that side as its foot. Also, the altitude having the incongruent side as its base will form the angle bisector of the vertex. It is common to mark the altitude with the letter H, often subscripted with the name of the side the altitude comes from. In a right triangle, the altitude with the hypotenuse C as base divides the hypotenuse into two lengths P and Q. If we denote the length of the altitude by HC, we then have the relation for acute and right triangles. The feet of the altitudes all fall on the triangle's interior or edge. In an obtuse triangle, the foot of the altitude to the obtuse angled vertex falls on the opposite side, but the feet of the altitudes to the acute angled vertices fall on the opposite extended side, exterior to the triangle. This is illustrated in the diagram to the right. In this obtuse triangle, an altitude dropped perpendicularly from the top vertex, which has an acute angle, intersects the extended horizontal side outside the triangle. Orthocenter. The three altitudes intersect in a single point, called the orthocenter of the triangle. The orthocenter lies inside the triangle if and only if the triangle is acute. If one angle is a right angle, the orthocenter coincides with the vertex of the right angle. The product of the distances from the orthocenter to a vertex and to the foot of the corresponding altitude is the same for all three altitudes. This product is the squared radius of the triangle's polar circle. The orthocenter H, the centroid G, the circumcenter O, and the center N of the 9-point circle all lie on a single line, known as the Euler line. The center of the 9-point circle lies at the midpoint between the orthocenter and the circumcenter, and the distance between the centroid and the circumcenter is half that between the centroid and the orthocenter. The orthocenter is closer to the incenter than it is to the centroid, and the orthocenter is farther than the incenter is from the centroid. In terms of the size A, B, C, in radius r and circumradius r, the isogonal conjugate and also the complement of the orthocenter is the circumcenter. 4 points in the plane such that one of them is the orthocenter of the triangle formed by the other three are called an orthocentric system or orthocentric quadrangle. Let A, B, C denote the angles of the reference triangle, and let A equals BC, B equals CA, C equals AB, be the side lengths. The orthocenter has trilinear coordinates and barycentric coordinates since barycentric coordinates are all positive for a point in a triangle's interior, but at least one is negative for a point in the exterior, and two of the barycentric coordinates are 0 for a vertex point. The barycentric coordinates given for the orthocenter show that the orthocenter is in an acute triangle's interior, on the right-angled vertex of a right triangle, and exterior to an obtuse triangle. Denote the vertices of a triangle as A, B, and C and the orthocenter as H, and let D, E, and F denote the feet of the altitudes from A, B, and C respectively. Then, The sum of the ratios on the three altitudes of the distance of the Orphic center from the base to the length of the altitude is 1. The sum of the ratios on the three altitudes of the distance of the Orphic center from the vertex to the length of the altitude is 2. The product of the lengths of the segments that the Orphic center divides an altitude into is the same for all three altitudes. If any altitude, say AD, is extended to intersect the circumcircle at P, so that AP is a chord of the circumcircle, then the foot D bisects segment HP. Denote the Orphic center of triangle ABC as H. Denote the side lengths as A, B, and C, and denote the circumradius of the triangle as R. Then in addition, denoting R as the radius of the triangles in circle, RA, RB, and RC as the radii of its X circles, and R again as the radius of its circumcircle, the following relations hold regarding the distances of the Orphic center from the vertices. The directrices of all parabolas that are externally tangent to one side of a triangle and tangent to the extensions of the other sides pass through the Orphic center. A circumsonic passing through the Orphic center of a triangle is a rectangular hyperbola. In any acute triangle, the inscribed triangle with the smallest perimeter is the pedal triangle of the Orphic center. The sides of the pedal triangle of the Orphic center are parallel to the tangents to the circumcircle at the original triangle's vertices. Orphic Triangle. If the triangle ABC is oblique, the points of intersection of the altitudes with the sides of the triangle form another triangle, ABC, called the Orphic Triangle or Altitude Triangle. It is the pedal triangle of the Orphic center of the original triangle. Also, the incenter of the Orphic Triangle is the Orphic center of the original triangle. The sides of the Orphic Triangle meet the sides of its reference triangle at three collinear points. The Orphic Triangle is closely related to the tangential triangle, constructed as follows. Let LA be the line tangent to the circumcircle of triangle ABC at vertex A, and define pound and LC analogously. Let A equals pound LC, B equals LCLA, C equals LCLA. The tangential triangle is A, B, C, whose sides are the tangents to the reference triangle's circumcircle at its vertices. It is homothetic to the Orphic triangle. The circumcenter of the tangential triangle, and the center of similitude of the Orphic and tangential triangles, are on the Euler line. The Orphic triangle provides the solution to Fagnano's problem, posed in 1775, of finding for the minimum perimeter triangle inscribed in a given acute angle triangle. The Orphic triangle of an acute triangle gives a triangular light root. Trilinear coordinates for the vertices of the Orphic triangle are given by equals 0, sec B, sec C, B equals sec A, 0, sec C, C equals sec A, sec B, 0. Trilinear coordinates for the vertices of the tangential triangle are given by equals minus A, B, C, B equals A, minus B, C, C equals A, B, minus C. For more information on the Orphic triangle, see here. Some additional altitude theorems. Altitude in terms of the size for any triangle with size A, B, C and semi-perimeter S equals 2. The altitude from side A is given by this follows from combining Heron's formula for the area of a triangle in terms of the sides with the area. Formula times base times height, where the base is taken as side A and the height is the altitude from A. In radius theorems consider an arbitrary triangle with sides A, B, C and with corresponding altitudes h, h, b, and hc. The altitudes and the encircle radius r are related by circumradius theorem, denoting the altitude from one side of a triangle as h, the other two sides as b and c, and the triangle's circumradius as r. The altitude is given by interior point if p1, p2, and p3 are the perpendicular distances from any point P to the sides, and h1, h2, and h3 are the altitudes to the respective sides. Then area theorem, denoting the altitudes of any triangle from sides A, B, and C respectively as and denoting the semi-sum of the reciprocals of the altitudes, as we have general point on an altitude if E is any point on an altitude AD of any triangle ABC. Then feet of the altitudes. The lines connecting the feet of the altitudes intersect the opposite sides at collinear points. Special case triangles. Equilateral triangle. For any point P within an equilateral triangle, the sum of the perpendiculars to the three sides is equal to the altitude of the triangle. This is Viviani's theorem.